to the same side, this is come to plus sign. I'm sorry. So this is plus sign. This is minus sign. Okay. So this is plus, this is minus. Okay. Thank you for the correction. Okay. So I will move on. Okay. Even though I have a lot to say about the characteristic, because characteristics is an amazing idea, right? And you can have a lot of physical interpretation of characteristics, especially when you consider the wave equation, the wave phenomena. So characteristic actually is the propagation path of the wave. Okay? But I really don't have time to say much about that. So I have to move on. Okay, so the next section is about to solve heat equation. Okay, by Fourier series. Okay. All right. So so we think about we have a bar. Okay. From x equals to 0 to x equals to L. So the length of the bar is L. Okay. And so this is the bar under consideration. Okay, and we have assumptions. One, that we have a thin metal bar or wire of constant cross section. Okay, so the cross section, if you make if you use a paper, right? Cut here vertically, the cross section were all the same, right? This is cross section, all the same. Second, we have a homogeneous material. Okay, so the material will be homogeneous. And third assumption is that we have perfect insulation. So perfectly insulated laterally, so that heat, okay, flows in the x direction only. Okay, so that means that we can consider the one-dimensional heat equation. Okay, so that the heat can only flow along the x directions, because we assume that laterally this bar has perfect insulation. For example, think about that you can have some material, right? And this material is very good to share the heat flow. Okay. Okay. So with these assumptions that so we let U to be the temperature. Okay. depend only on x in addition to the temp T. Okay, so U actually is a function of x and T. So U is the temperature. And then as derived in section 12.5. Okay, so please go to see section 12.5. U is governed by the one-dimensional heat equation. So the first derivative of U with respect to the temp is equal to C squared times the second partial derivative of U with respect to X. Okay. Okay, and we will consider assume two boundary conditions. That U0T equal to 0 and the ULT equal to 0 for all t greater than 0. This is 12.612. Okay. By keeping the temperature zero at the two ends of the bar. Okay, so we will assume the two boundary is zero temperature. And one initial condition. U of x is 0 is equal to f of x. Okay, and here f of 0 is equal to 0 and f of L equal to 0 due to 12.612. Due to the boundary condition. Okay? So this is the boundary conditions. And so the initial condition here, f of 0, f of L are both zeros. Okay? So you may think about that. Initially, the bar has some temperature distributions along the bar from x equals 0 to L. Okay, so you have the temperature initially. And then, because you have temperature, and basically you have different temperature along the bar, so you have a gradient. All right? And so it will produce heat because because the system has the tendency to go to the equilibrium. All right, so you have the heat, and since the both end kept the temperature is 0, okay, then it's 0, so that if you have high temperature here, higher than 0, then your heat go to both ends. But if the temperature is negative, then your heat flow from both ends into the bottom. Right? So you can see about that. So this is the heat flow. So this is the physical phenomenon. So any questions before we actually solve the wave equations with two boundary conditions here and one initial condition? Any questions? Okay. So again, we will follow the procedure as we did in section 12.3. So step 1, the method of separating a variable to obtain true ODEs. Okay? So basically we use the method of separating variables to transform the PD to ODEs. Alright, so we let uxt equal to f of x and g of t as before. So now, as before, this is f of x, and okay. Alright, and so we have okay. So that we have f of x is gt, which is ut, and ut is equal to c square uxx. So this is c square gt and the square f of x dx. All right. So that implies that 1 over c square gt and gt equal to 1 over f of x f of t square f of x and d, which is equal to k. Okay. So that we have f sub prime minus kf equal to 0, and then g prime minus k c square g equals 0. Okay, so the first one is the second order ODE, but the second one is first order ODE. Okay, so it can be seen that for k equal to 0 or k greater than 0, the only solution we have only trivial solution. to 0. Okay? But for negative, okay, t squared, we have f of prime plus t squared, f equals 0, and the g prime plus k t squared, f t squared. So we have p c squared g equals 0. Yeah, okay. So we have 12.6.4, 12.6.5. Okay. All right. So now we will solve the two of these. So step 2, solving the ODE. Satisfying the two boundary conditions. In 12.6.2, okay? The two boundary conditions here. Okay, now from the boundary condition, in 12.6.2, okay, we have u0 t equal to f0, gt equal to 0, and we have u lt equal to fl, and g equal to 0. Okay, so this is one. To find non-trivial solutions, we must have gt not equal to 0 for some p. Okay? So this is implies that this is true for. Okay? So we know g of t is non-zero for at least one p. So this is implies that f0 equals to 0 and fl equals to 0. Okay? Now, so from 12.6.4, this one, we have a general solution. F of x equals to a cosine px plus b sine px. Okay? But f0 equals to 0 implies that a times 1 plus b times 0. So imply a is 0. Okay? Alright? So we have f of x equal to b sine px. With b not equal to 0, because if b is 0, then f is 0. And our solution u is 0. Okay? Which is trivial, and we don't want trivial solution. Now, FL equal to 0 implies that sine PL equals 0. So it implies that P is equal to m pi divided by L, and this 1, 2, 3. That's before. Right? So this is equal part, right? So we let f and x to be sine m pi x divided by L, or n equals positive integers. Right? And then now, for p equal to m pi divided by L, okay, we solve. Okay, so this is g sum plus c m pi L squared g 0. 12.5 becomes, okay, so this equation becomes this one. Okay, so we define this lambda n equal to c m pi L. So the general solution, okay, it's Gn T equal to Bn E minus lambda n squared T. Okay, so this is 1 for n. Okay, so we had experience before, so now, so all the derivations quite standard, right? So hence, un xt fn x gmt, okay, it's bn sine n pi x divided by L exponential minus lambda n squared t for n in the set of all positive integers. So or solutions, okay, of the heat equation in 12.6.1 and satisfying the two boundary conditions. Okay, in 12.6.2. So each solution, okay, un xt is a solution of the heat equation and satisfying the two boundary conditions. So, and are called eigenfunctions. Okay, of the problem, and corresponding to eigen values of lambda n equal to c n pi divided by L. Okay. Now we have one initial condition, right, to consider. So, so step 3, solution of the entire problem with Fourier series. Okay. So again, since the heat equation and the two boundary conditions are homogeneous and linear. Okay. We can superpose of the eigenfunctions. So we take the superposition of the eigenfunctions. This is Bn and sine pi and pi x divided by L exponential minus lambda n squared t. Okay. So this one, okay, also satisfy 12.6.1 and 12.6.2. Provided that the series converge. Okay, so now the initial condition in 12.6.3 dictates the following: ux0 is equal to summation b n sine n pi x L equal to f of x, which is just the Fourier sine series expansion of f of x. So we know how to find the coefficient again. Okay. Right. So we find that. So the existence and the uniqueness of the solution can be established. Okay? By assuming that one, f of x is a piecewise continuous. Okay. The second, f of x is one-sided derivatives. Okay, at all interior points of the interval 0L. Any questions? Alright, so we solve heat equations assuming that the two endpoints has temperature kept to be 0, right? So to be 0. Now, how about the condition that both and you can have temperature 0 at 2n because you have a buffer, a heat buffer, right, at both ends. Okay, such that either the heat flow into the buffer or heat flow out of the buffer to maintain that the temperature is 0 at both ends. But how about the condition that both ends of the bar, okay, are insulated? Okay? Means that it is impossible for heat to flow out or in, right? At the 2 points. So you know that in physics, the rate of the heat flow, okay, proportional to the gradient of the temperature. So, hence, if the ends x equal to 0 and the x equal to L are insulated, okay, means that no heat flow. Then we must have so we must have ux 0t to 0 and ux t is 0 for all t greater than 0. Okay, so the gradient means in here we have only one dimension. So this is just the first partial derivative of u with respect to the x-axis, right? So this is the gradient is 0 because you have no heat flow. So at both ends you have no heat flow. So the boundary condition, right? The two boundary condition becomes 2 is 2. Okay, so now we have two boundary conditions in terms of the first partial derivative of u with respect to x. Okay. Okay, so this implies that the d of f is x 0 and 0. Okay? Okay? So this implies that we must have got that f prime equal, so f prime is 0 and f prime is 0. Okay. So so now we have different boundary conditions. Okay. So two different boundary conditions for the ODE of f of x. So f of k, f equals 0. Okay, so we have two boundary conditions f and 0 here. Okay, and so that so with k equal to 0, we have f of x equal to ax plus b. Okay, right? And this implies that because the first derivative should be 0, and the first derivative is equal to a, so it implies a equal to 0. So that f0 we define to be 1. Okay? The constant is a solution. Okay? It's a solution. Of the wave equation. No. Of it's a solution of 12.6 what? The ODE, which is okay, 4. Yeah, thank you. Okay, 4. Okay, and satisfying the new boundary conditions. Okay. All right. So for k equal to 0. We have solution, non-trivial solution. Now with k equal to minus p squared equal easy. So when k is negative, again, we have f of x equal to a cosine px, b sine px. Okay? So implies that f prime fx equals sine px px. Okay? Now the two boundary conditions implies so 0 equal to f prime 0. Okay, prime 0 implies that 0. So this implies that b is equal to 0. Okay, so f of x is not equal to a cosine p of x. And with this f prime of x equals a sine px. Okay? So 0 equal to f prime L implies that with a cannot be equal to 0. Okay, and so you have PL implies that P equal to N pi F. This is P. And then 1, 2, 3, etc. So now, because of the insulation at both ends, now we find that our solution should be cosine and pi x and L, and n equal to 0, 1, 2, 3. Okay? So now we include n equal to 0. Okay? Because when n is 0, this is 1. This is 1, okay? And by solving 6.5, we have Gn T equal to An. Again, right? N is equal to 0, 1, 2, etc. Oh yeah, number n again is Cn pi divided by L. So U xt Un xt x become 2 An cosine m pi x divided by L e minus number n squared t for n. Sub 0 means that okay, so n sub 0 means all non-negative integer, right? The set of all non-negative integers. Okay, and so the solution of the entire problem is u of x from 0 to infinity An cosine n pi x divided by L e minus lambda n squared t. Okay? With the initial condition in 12.6.3, we have u x 0 equal to n from 0 to infinity An cosine n pi x divided by L, which is equal to L. Okay, so which is the Fourier cosine series expansion of f of x. So now we need the Fourier cosine series expansion. And we know An. So An is so we have to set A0 is equal to 1 over L, 0 to L, f of x dx. And the An is 2 divided by L, 0 to L, f of x cosine pi x dx. For all n belongs to the set of all positive integers. Okay, so we solve okay, so basically we have solved the one-dimensional heat equations. And so we can extend the technique to solve the two-dimensional heat equations. Okay, oh, well, time is up, so I better finish at this point. And I probably know some of you will have an examination after that. Yeah. So. So, do you have any questions? Okay. So I will see you.